Just as we can manipulate the scale of graphs of univariate data, we can also manipulate the scale of graphs of bivariate data, possibly resulting in incorrect conclusions. Therefore, numerical summaries of bivariate data should be used in addition to graphs to determine any relation that exists between two variables. So we just worked on graphs. We're going to work on numerical summaries next. So this basically says that you should use both instead of one or the other. So this numerical summary is going to be our linear correlation coefficient. This is number 3 on our calculator sheet. Make a scatter plot with a linear regression line. And it is denoted by lowercase r. The linear correlation coefficient is a measure of the strength and direction of the linear relation between two variables. As a side note, you can always use the calculator even when the homework will say do by hand. I'm fine with you doing it all on your calculator. So let's match the following with the graphs A through F below. So which points align in a straight line with a positive slope? This is a straight line and the slope is positive. So that'd be D. Second one, straight line with a negative slope. That's A. They do not align in a straight line, but still have a positive slope. That's E. Do not line in a straight line, but have a negative slope. That's B. They do not align in a straight line and have no linear relation. That would be C and F. Note that F does have a relation, it's just non-linear. Here are the properties of linear correlation coefficients. So the linear correlation coefficient, R, is always between -1 and 1. Okay, so you can see here, the R's are always between -1 and 1. If R equals +1, then a perfect positive linear relation exists. If R equals -1, then a perfect negative linear relation exists. The closer R is to +1, the stronger is the evidence of positive association between the two variables. And then the closer R is to -1, the stronger the evidence of negative association between the two variables. If R is close to 0, then little or no evidence exists of a linear relationship between the two variables. So a value of R close to 0 does not imply no relation, just no linear relation. And you could see that here in C and F. So again, F has no linear relation, but it does have some kind of a relation. The linear correlation coefficient R is a unitless measure of association. So the unit of measure for X and Y plays no role in the interpretation of R. The correlation coefficient is not resistance. Therefore, an observation that does not follow the overall pattern of the data could affect the value of the linear correlation coefficient, which makes sense. So if I put a point here, a big point, your R will no longer be +1 because now you have to account for this point.